This video is entitled Chain Rules for Functions of Several Variables. Alright, well, let's see what we have here. So now we're taking chain rule ideas from single variable calculus and expanding them out to multivariables. So let's look at chain rule where you have one independent variable. So we're saying let W equal a function of x and y. I'll go over here, and x is the function g of t. So that's what we mean by the one independent variable, and y is h of t. So w is a function of both x and y, but x and y are both functions only of one variable, t. And then here's the formal definition of dw dt. So ultimately we're trying to find the derivative of w with respect to that variable t. So dw dt is essentially the partial of w or partial of x. See, obviously when a function's written as more than one independent variable, it has to be partial derivative notation. So partial w, partial x, but it's okay for this to say dx dt because x is only a function of one variable t. So that's why the notation is different. Partial of w respect to y times dy dt. I'm not sure if this function, this little diagram, helps you in any way, shape, or form, but I'm not going to spend any time with it. But if that helps you, then that's terrific. Now, the way I'm going to actually handle these problems is without using that chain rule, is you can substitute before differentiate, which I find to kind of sort of be easier, and you're not required to use that chain rule, meaning that so if x is a function of t and y is a function of t, I will just substitute both of those results into this function w, and that way then everything will be in terms of t, and you can just take the derivative of w with respect to t directly that way. I mean, unless it's turned into some big mess or something, but it shouldn't. I mean, at least I won't pick problems that would be that bad. In fact, I even just noticed that I crossed out here. So when you see a problem on an exam, it says, find by the chain rule, if I forget to put, or substitution or whatever, you're free to do it this way, every time. You don't have to specifically use the chain rule. The chain rule just kind of shows from a theoretical standpoint how it develops, how it maps out. So let's take a look at this number 6. Here's an example where w equals cosine of x minus y, where x equals t squared and y equals 1. So what I'm going to do is I'm going to take x equals t squared and put it right in there for x. Y equals 1, I'll put that in there for y. And then w just becomes cosine of t squared minus 1, and then you can just take the derivative of that with respect to t. So dw dt would be, so the derivative of cosine is negative sine, and then you got to take the derivative of the inside, don't forget. So that's going to be 2t, so I just kind of put the 2t out in front with a negative. So it would be negative 2t sine of t squared minus 1. Let's take a look at this number 8. So we have w is xy cosine z, and the definition did not mention that it could be more than two independent variables, but it can. The chain rule can't extend to more than two variables. So this is three variables, x, y, and z. But the same idea applies, though. All of those functions, if it's more than two, they can only be a function of t right now. We're going to look at chain rules of independent variables coming up shortly. So if you substitute, put in t for x, put in t squared for y, and put an arc cosine of t for z. So you have t times t squared, and this knowing your trig comes in real handy here. I mean, you could actually do this, with just regular derivatives, but this is just so much simpler if you do this. Is that cosine of arc cosine of t are inverse functions. So therefore the answer is just going to be t. So all you have is t times t squared times t, which makes t to the fourth. And that, tidies up, cleans up real nicely. So then now all you're doing is taking the derivative of t to the fourth, which then becomes 4t cubed. Now the next one, I won't read the problem again this time. I'll just skip over that. But so all I'm doing is taking x and y and z and substituting them in right here on this. Right. So t squared goes in for x, y. So it's 2t all squared, and then plus t squared squared times z here, which is 2, and then 2t, which is y, times 2 squared, which is z squared. So you end up with this is a 4t to the fourth. This is the 2t to the fourth. You add those together, you get 6t to the fourth. And then this becomes 8t right here. So that simplifies quite nicely. So the derivative of that would just be 24t cubed plus 8. So how about that? That's not bad. Let's take a look at, I went up here and took problem 8 here and showed how it would be done the other way. So obviously I'm taking something that was simple and now showing the harder way of it. So you do not have to worry about this, but I went through this and the purpose of the triangle was for me to come up with a way to identify the values for sine of arc, to come up with sine of arc cosine of t, because I still needed everything to be in terms of t. Now, so it does kind of, once you get that part done, it does kind of clean up quite nicely, and you end up working your way into t cubed plus 2t cubed plus t cubed, which is 4t cubed, which is the same answer we got doing it by the substitution method. But I definitely think the substitution method was much, much better there. All right, so chain rule of 2 independent variables. So now suppose that w is a function of x and y, which it still could be more variables than just 2 here. The 2 comes from this part right here. Now we're saying x can be a function of 2 variables, s and t, and then y would be s and t. So even though that the w could be, it's at least 2 variables, or it could be more, the restriction is that whatever these are, if it was x, y, z, whatever the case may be, they're consistently all 2 variables there. I mean, yeah, you couldn't have, it'd be a mess if they had different numbers of variables there. Well, actually, it would kind of not satisfy the rule here, so to speak. So, okay, so let's see what we have here. Here it is in just formal form, but we're going to use substitution again. I'm not a big fan of using s there, frankly. I mean, I wonder if I might have done a problem with s. No, it looks like I didn't, because I kind of took those out. Because the problem is you have to be careful when you're writing an s, because it looks like a 5. But that's all right. I like this with u and v, and we're actually going to do one with r and theta here in a minute. Use a polar coordinate deal. So now this is all partial stuff here. Remember the last problem had part of it was partial, part of it was d something, d whatever. Well, all these are partials, because w is a function of more than 2 or more variables, and then these are all functions of 2 variables. So everything has to be written as a partial for this. So partial w with respect to s would be partial of w with respect to x times partial of the x with respect to s, plus partial of y, w with respect to y times partial of y with respect to s. And then the same thing, these just change to everywhere there's an s in this formula, just changes to a t for the other formula. So let's take a look at this one. W equals sine of 2x plus 3y, where x equals u plus v, and y equals u minus v. So I'm going straight substitution here, just like we had before. So we take, so you have 2, so we're looking for both these. Oh, and then we're actually, so sometimes it might ask you to do it at a numerical value for your variables. Okay, that's fine. Obviously, you know, you can get the derivative in terms of just the variables, and you also can evaluate it at a point. Just depends on whatever the problem's asking. So sine of 2x would be sine of 2 times u plus v. So, you know, that's going to be 2u plus 2v. And then plus 3y, which is u minus v. So it's 3 times u minus v. So you have a 2u plus a 3u will be 5u. And then a 2v minus a 3v will be negative v. So when you substitute, then your function w becomes sine of 5u minus v. So let's take the derivative with respect to u and v. And see what happens here. So the derivative, of sine is cosine, and then the derivative of the inside with respect to u would be 5. So it's 5 cosine of 5u minus v. And then the derivative with respect to v, the derivative of sine is cosine, and then the derivative of minus v is negative 1. So keep in mind, this negative is coming from the derivative of negative v, not from the sine. So you might have first looked at this and go, wait a minute, he doesn't know that the derivative of sine is positive cosine. Well, I do know that, but so sometimes that could be confusing, but that's not where the negative is coming from. So it's coming from the derivative of negative v. But the derivative is still positive cosine. Okay, the rest of this is just plugging in the 0 and the pi over 4. So you get 5 square root of 2 over 2 for the partials for this one right here, respect to u. And then you'll get negative root 2 over 2 for the value at partial respect to v at that point, 0 pi over 4. So the key is, if you get, as long as you get the partial of w respect to u and the partial of w respect to v, you pretty much have it, you know, taken care of. So that's the only other step you might have to do would be multiplying, you know, or substituting a numerical value. But if not, that would have been it right there. All right, this one looks interesting. So here we have this function, and x is r cos theta, so y is r sine theta. So you see that w then is a function of x and y are both functions of r and theta. So it does satisfy that criteria, but we're going to substitute. So I want to put in r cos theta for x, r sine theta for y. So when I do that right here, I get minus 5r squared. Now, I guess I sort of skipped a step here, but what I did is I factored out a minus 5r squared, and it's going to leave cosine squared plus sine squared. That's what makes this, you know, catching this is what makes this problem key. I mean, yeah, you could still take the derivative without simplifying that, but it would be a lot messier, a lot more trouble. In other words, if you just left it as minus 5r squared cos squared and then minus 5r squared sine squared, yeah, you could do that. It would be a lot harder. Because the beauty of that is when you factor this cosine squared plus sine squared out, that is a value of 1, so it goes away. So that means w just ends up reducing to be only a function of r. Theta is not involved. So the partial of w with respect to r then, bring down the 1/2, leave the inside alone, subtract 1 from the exponent makes it negative 1/2, and then the derivative of the inside with respect to r would be negative 10r. I guess all I did here was just divide the 2 into the 10. Obviously, it's not wrong if you don't do that, but that's what I did. All right. Now, The partial of w respect to theta is kind of interesting. We haven't had this happen yet, but that's why I like this problem, to show that it is possible. Well, notice that your function, once it's changed to r and theta, w has no thetas. So obviously the partial respect to theta then would be 0, because in terms of theta, that's just one big constant right there. So it ends up being 0 because there's no theta. Chain rule, implicit differentiation. Now the top one that doesn't involve the partial formulas there, the top one is essentially this. When we talk about implicit differentiation, it's the same thing you would have done, back in Cal 1. So after you see this way to do it, you're probably going to wonder, why didn't we do it this way back in Cal 1? Well, the problem with that is, to do it this way, you would have to have known partial derivatives. So that's why, that couldn't have done it this way. So if you have your f of xy equals 0, in other words, written implicitly in form, equals to 0. So it's not like, in other words, y is not a function of, or z is not a function of x and y. Everything's written, when you see this big F, that's generally implicit notation. We're going to set that equal to 0. Actually, I think you could leave it a constant over here on the right side, and that would not matter, like if it was set equal to 5. But I guess we'll go ahead and just follow this just to be on the safe side, but it won't matter. The key is that all the x's and the y's need to be on the same side of the equation. That way we don't have any sign errors when we take the derivative. All right, so this formula just says for implicit differentiation, we take the negative of the big fx partial over the fy partial. So we do the fx partial divided by the fy partial, put a negative out in front of it, and we got it. Of course, you could apply the negative to either the numerator or the denominator if you wanted to, or not both, obviously, just one or the other, or you can leave it just sitting on the outside. And of course, this is implying that the fy partial is not 0, because of course that would be divided by 0. Let's see what we have here. And let's do this one, then I'll come back and look at the next rule. Let's wait till we try this one out. Now this first example, I'm showing you how to do implicit, formal implicit differentiation, like it would have been done back in Cal 1. I'm just showing you how it would have been done, and I'm going to show you how it's then done using this rule that uses partial derivatives. So remember when you do this, that every time you take the derivative of a y term, you have to indicate a derivative in there. Now you might have learned it with dy dx. Don't let that bother you if you did. That's fine. A lot of instructors will do it with dy dx. Maybe I'm on the lazy side, so I just like to put y prime. But it's the same thing as it would have been dy dx. So the derivative of 2x squared would just be 4x. Now the derivative of negative 3y cubed would be negative 9y squared y prime. Anytime you differentiate a y, you have to put y prime there. Now the next one, we've got a product rule. So remember you have two orders for the product rule, so I'm kind of going f prime g. I'm starting with that order. So the derivative of x would be 1, and then y squared is just y squared, no prime, because we're not taking the derivative of y squared. We're about to, though. Plus f, which is x, times g prime. So the derivative of y squared would be 2y, then y prime. And of course, the derivative of minus 5 is just 0. So what you want at that point, it doesn't matter whether you go left or right, but you want to get the y prime terms on the same side of the equation, either the left side or the right side. So it looks like I chose to add the 9y squared y prime and bring it over here, and then subtract the y squared and brought it over to the left side. So that's one of two correct ways to do it. Then at that step, you would the next step be, the purpose of that, having the y primes all on the same side, is so you can factor out a y prime, which is what I did in the next step. I factored out a y prime, and then divided by what was factored out. So the 2xy plus 9y squared is what was factored out. That will just go in the denominator of the left side. So that means, using regular implicit differentiation, y prime would be 4x minus y squared over 2xy plus 9y squared. Now, using this theorem, using it with partial derivatives, see, I'm denoting that the big fxy means I brought everything over to one side and left 0 on the other. So I had to, so what I basically did was I brought the minus of the xy squared over, made it minus, brought the minus 5 over, and made it plus. So now we need the fx partial and the fy partial. So the fx partial, the derivative of 2x squared would be 4x. There's no x term here, so that's 0. The derivative of negative xy squared, the x goes away because the derivative is 1, so it makes it minus y squared right here. Now the fy partial is, there's no y there, so that's gone, negative 9y squared, and then the derivative of y squared is 2xy, and then with the negative in front, so there's your 2xy. And then so we plug it into the formula. There it is. It's the negative of f, you don't have to have the parentheses, but it's the negative of fx over fy. And we have negative of 4x minus y squared over negative 9y squared minus 2xy. Now this answer, especially if it's a handwritten answer, this is perfectly acceptable. And it does match that other answer, which you don't have to do this, obviously, but I just want to mention. So the negative on the outside could be applied to either the numerator or the denominator if you wanted to. You don't have to, but I'm just mentioning that because if you apply the negative to that denominator, then you see it looks exactly like that answer. It doesn't mean it was still equivalent already. It was still correct, but it just makes it look like that other one now. So. All right, so let's try another example of that, then we'll go back and look at that other implicit rule. Okay, so let's see what this one says. Sec xy plus tan xy plus 5 equals 0. It's going to be a little careful with this one. It's already written in implicit form there. So the derivative of secant is secant times tangent. Essentially, the derivative, in other words, of sec u would be sec u tan u u prime. Let's see. So then the partial respect to x, so now will be sec u, so it'll be sec xy tan xy times the derivative of xy with respect to x. So that x goes away as 1, so it's going to give you y. And therefore the derivative of tangent is just sec squared, but same kind of scenario, it's sec squared of xy times that derivative with the inside respect to x. And that gives me y again. Then fy is essentially the same thing, except the derivative of the insides now will be x instead of y. That's the only difference. Now this answer is going to look ugly, but we're not trying to solve for anything. That's the key. You're not trying to do, with the original implicit differentiation, you were doing some algebra to solve for, to get y prime by itself, blah, 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 and all that. We don't need that here. So don't try to oversimplify it. Don't simplify at all, really. I mean, unless you just saw something obvious, but here it looks like something, So the derivative is just going to be negative fx over xy. So it's the negative of this top one over that bottom one. I guess the one thing that could be done, but I still wouldn't even worry about it, is you could factor out a secant from all four of those terms, and it would reduce by that, but I don't think that's even worth bothering with, frankly. But the main thing is we got the partial derivative. We got dy dx using the partial derivative formula. That would have been a messy one using implicit differentiation. Boy, that would have been a rough one. I think we would have gotten it though, but... So number 24, let's go back and just take a look at that one. See, oh yeah, see 24 was technically not in the implicit form, so I brought the 6 over. But like I was saying earlier, as long as it's only a constant over there, it's not really going to matter, but I might as well, follow the appropriate definition. So for this one, I chose not to worry about quotient rules, so I just brought the x squared plus y squared up to the top and made it a -1 exponent. One reason I chose to do that, well, the quotient rule was one, but another reason is that whenever I do the fy partial, see, the first one's going to be a product rule for sure, because you have something with an x multiplied by something else with an x. But when we get to the fy partial, remember that x behaves as a constant. So all I'll just have to do is a power rule. I don't have to do any kind of... So that's better than doing, 2 quotient rules, especially when one of them was not needed, because the derivative of the top with respect to y is 0. But we do need a product, or like I said, quotient rule would have applied, but the way I wrote it, we're going to go product rule. So if I go f prime g, the derivative of x is 1, and let's see. I went f prime, fg prime. That's weird. I usually go, I wrote it right out here. Okay, thank goodness, because my normal instinct's to go f prime g. So anyway, so let me stand corrected here. So actually the x is there because it's that x for f here, and then g prime, you bring down the -1 right here, and decrease that exponent by -1, and then you take to make it -2, decrease it by 1 to make it -2. The derivative of the inside is 2x, and there you go. I guess you could combine those x's together, but not that big a deal. And then plus f prime g, so the derivative of x would be 1, nothing there, and then just g itself right here. So there's your fx. Fy, I'll just remember I had no quotient rule, and that, of course, these two terms, had no x in them. So this one, you just bring down the -1, subtract 1 from the exponent to make it -2, take the derivative of the inside with respect to y, so it'll be 2y, and then minus the derivative of y squared, which is 2y. And I could move those terms around a little bit. Don't cancel those 2 y's, obviously, because the first 2y is multiplied by that other stuff. Let's see if I did that. No, I didn't even bother to do it down here, which is fine. No need. I left it as is. Let's see. Even with negative exponents, that was also fine. Leave it that way. So, I might have cleaned up a little bit, but it's not worth the hassle of even doing it, frankly. I just want to make sure that we can get it done correctly, and you probably won't have anything this bizarre on an exam anyway, so as long as you just know your basic derivatives and can handle the idea, you'll be fine. Let me go back up here. I did copy those rules, but let's take a look at so if it's defined implicitly in terms of x, y, and z, and then you want the derivatives for z, there'll be 2 of them. There'll be partials in this case. Obviously, when there's 2 variables, y as a function of x means dy dx. But z in terms of x and y means partial of z respect to x, partial of z respect to y. So obviously, you should put these formulas on your note sheet. Note sheet. Or if I've changed my way I teach to go back the way I used to do it, let me say that, if I'm providing formula sheets. But somehow, you don't have to memorize it either way, so somewhere down the road, I might go back to giving formula sheets instead of allowing a personal note sheet. But either way, that's should not have to be memorized. And then here they are, copy down here. So it's basically negative fx over fz, and then negative fy over fz. So even though I wrote the negative in the numerator, the negative obviously could still be to the outside. It doesn't have to be in the numerator. I don't know why. It doesn't matter. It's mathematically equivalent. That's all that matters. But so in other words, it's not different. Oh, yeah, okay, the formula writes it with the negatives out in front, you know, when it did it down there, but okay. I don't know. Not a big deal, obviously. So we want to find the partial of z respect to x, partial of z respect to y. So first thing we have to do is move everything over, set it equal to 0 to get it in implicit form, which I did right here. Okay. That's good. And let's see what we have. So now I'm just showing up saying, yeah, it's in this form right here. Verified. So I did FZ first because FZ is actually going to be the denominator for both of these results. The same denominator, just different numerators. So let's take the derivative of this form with respect to z. So z cubed would be 3z squared. 2x y squared has no z, so it's gone. Negative natural log of z would just be negative 1 over z. And then there's your z right here for this one. So the derivative of z squared would be 2z. So I just brought the 2 right in front. X cubed y4 just stay as is. So it would be 2x cubed y4th z. So there's your denominator for both answers. And now let's get the two numerators, fx. So the x partial, there's no x here, that goes away. The derivative of this x is 1, so that gives you 2y squared. Z, this one doesn't have an x here, but this term does. So it'd be the derivative of x cubed would be 3x squared with a minus there. So it'll be 2y squared minus 3x squared y fourth z squared. That's your fx. And then fy would be, no y here. Bring down the 2, makes that 4xy. No y here. The derivative of y to the fourth would be 4y cubed with a minus in front. So you have 4xy minus 4x cubed y cubed z squared. And then so for the partial of z respect to x, put that on top, negative of, I just left the negative. Obviously you can distribute the negative, whatever the case may be. I just left the negative of, the way I wrote it like that though. If I didn't distribute the negative, I had to use parentheses there. Or I could have ditched the parentheses and put the negative out here to the outside. That would have been right. But the way I wrote it did require parentheses. So let's see, then same thing here. So it's the negative of this expression right there over that partial respect to z. So, all right, I don't think these are too bad. Just be careful with your derivatives. Looks like we've got a couple more coming up here. How about this number 30? Z equals e to the x sine of y plus z. So I went ahead and brought the right side over to the left side and made it z minus e to the x sine of y plus z. So once again, I need fx, fy. Looks like I did fz at the bottom here, but I'll do it first. But it's the denominator, remember? So let's see. So fz. Now, one thing I want to mention, I just noticed with this one, you look at this one, you might, if you looked at it not very carefully, you might think, well, isn't z already, in explicit form, meaning you could just take the partial derivatives the normal way, in other words. No, because see there, yeah, z is by itself over here, but notice there's a z in the parentheses of this sign, y plus z. So it's definitely implicit form. So the derivative of z is 1, and then the derivative with respect to z, e to the x would just stay as a multiplied constant, and then the derivative of sine of y plus z would be cosine of y plus z, and I just wrote the 1 there, which mathematically does not have to be there, but just wrote the 1 to show that I was acknowledging that that was the derivative of the z. You know, so I did not forget the derivative of the inside, which I guess, you know, would have been, you know, accidentally right if I hadn't have done it for this problem, but of course the minus comes from the subtraction. And then fx, see that's no x there, so so basically it's the same as this, because you're taking the derivative of e to the x here, which is e to the x. So the sine of y plus z has no x, but it is multiplied. So since it's multiplied by an x term, it stays there. If it was added or subtracted like the z here, it would differentiate away to 0. So the derivative of e to the x is e to the x, and then, yeah, it'd just be sine of y plus z. Now for the next one then, with respect to y, so now you have to take the derivative of this because there's a y there. So the derivative of sine of y plus z would be cosine of y plus z times the derivative of y, which is 1 with respect to y. And then the e to the x stays as a multiplied constant. So there you have it. Now just plug everything in. I just went ahead and decided to take the negative since these both had negatives. I went ahead and just since, oh, okay, that would be easy just to make it positive. But obviously didn't have to do that. And there we go. So how about this one? It's already in implicit form, so nothing needs to be moved around or anything. But let's see. So I'll do the FZ partial again first, even though it's the last one here. So the first term has no z. Second one does. The derivative of z would be 1, so it leaves a y squared. And the derivative of z squared would be 2z. So the denominator for both these answers will be y squared plus 2z. All right. Fx, partial. Only term that has an x is the first one. So the derivative of x is 1. So it's 1 times ln of y. Everything else goes away to 0. So it's just ln of y. And then the y partial, the first two terms have a y. So the derivative of ln of y would be 1 over y. So I just wrote that as x over y. Obviously, it's the same thing as x times 1 over y. And then y squared z would be 2yz. Right, so. And there, of course, the formulas both have the negatives there. So it's the negative of ln of y over y squared plus 2z, and then the negative of this one, the negative of x over y plus 2yz over y squared plus 2z. And that concludes the video for chain rules for functions of several variables.